All right. How y'all doing?
Good.
Glad to hear it. Any questions, needs, concerns, etc. before we get started? All right. Last time we were talking about torque still, looking at what happens when torque isn't balanced and when torque causes angular acceleration. We started looking at how a yo-yo spins as it falls. I'd like to do a different one as our main example for that real quick, kind of in place of the yo-yo. The yo-yo's just gonna take longer than I'd like, so instead of like switch gears and look at a related example instead, where torque causes angular acceleration. Welcome to Wheel of Fortune. You're a contestant on the show, and you're going to spin the wheel. The wheel itself is pretty big. It's got a radius of 2 meters and a mass of 45 kilograms. You're going to stand at the very edge of the wheel, apply 23 newtons of force to it to get it to spin. My question is, what will the wheel's angular acceleration be when you exert that force on it? We're going to consider the wheel to be a uniform cylinder, because a disc really is just a flat cylinder when you think about it. Conceptually, when you apply that force to the wheel, what are you doing? What is happening to that force?
If it's exerted onto the wheel.
Force is exerted on the wheel. Now the wheel's kind of bolted in place at the middle, so it's not going to linearly accelerate. Instead, that force is doing what to the wheel?
Spinning.
Spinning it. It's going to cause angular acceleration via torque. Note that when you spin this wheel or a bike wheel or anything, the force is exerted some distance away from the pivot. That radius is the radius of the wheel today. So whatever torque you're generating is going to cause the wheel to accelerate angularly. This is what we want to know, how fast it's going to accelerate because of our actions today. Two things that we need to find angular acceleration. One is the value of the torque. How can we determine the value of torque we generate? Yep, the other formula for torque. Radius 2 meters times the force we used of 23 newtons. As long as that force is totally perpendicular to, and redraw the line. As long as the force is perpendicular to the radius of the wheel, then that will generate torque, and that will tell us how much torque. Now we need to figure out I. Remind me what I stands for.
Inertia.
Moment of inertia, but yes, moment of inertia. It's weirdly not just inertia, because inertia happens whether you're spinning or not. Moment of inertia is the dedicated term for how mass wants to rotate. I appreciate that is odd, especially since we use the letter I, but we used the letter M a while ago. So we need to determine the moment of inertia of this object. We know that we can treat it as a cylinder, and as I kind of showed in that question, I will always tell you what shape you can consider an object to be. Wheels will pretty much always be cylinders in here, just for simplicity's sake. And since it's a cylinder, you can check either this chart or your formula sheet to note that specifically moment of inertia for a solid cylinder, not a hollow one, a solid one, is 1/2 times its mass times its radius squared. So that is what we can write in place of I. So our full formula when factoring in the specific version of I we want to use, and also the other formula for torque. It's going to be radius times force equals 1/2 times mass times radius squared, and then times alpha. How's that feel? All right. Now, as of this point, we know everything except alpha, so we're good to go just for plugging and calculating. 2 meter radius, force of 23 newtons, equal to 1/2, mass of 45, radius of 2 squared, equals alpha. The newest math disagree with 0.511. What were the units on that be?
Meters per second.
Almost. That would be linear acceleration. Alpha stands for angular acceleration, and how does that change the unit? Radians per second squared. Because this is a measure of how much its rotation changes while you're applying that force. So every second that you are grabbing the wheel and applying that 23 newtons, the wheel's rotation speeds up by 0.51 repeating radians per second. So if you're acting on it for 1 whole second, it speeds up from 0 to 0.511. If you apply it for 2 seconds, then that would be 1.022 radians per second. How do you guys feel? All right. Now, main thing for today, the last couple of concepts that I want to talk about for rotation. Moment of inertia is important because pretty much every single time we would use mass to calculate something linearly, its angular counterpart involves moment of inertia instead. So to compare the old linear formulas to the angular ones again, main ones to focus on: momentum equals mass times velocity. Therefore, angular momentum equals moment of inertia times angular velocity. And also, kinetic energy has mass in it, and likewise, its angular counterpart has moment of inertia in it. And those will be the last two things we look at mainly for the rotation chapter. So we're going to close out today looking at angular kinetic energy and angular momentum. Yes?
Is chapter 13 and 14, like, is that after our next test?
Yes.
Okay.
That is however many days of talking about waves and sound I can get in before exam prep.
Okay.
That's the whole thing.
Just making sure.
It might amount to one exam question, but it wouldn't be on test 2. Does that address the concern?
Yeah.
Yeah. Test 2 will be through chapter 9. 9 is pressure and buoyancy, which we'll spend a few days talking about next week before test prep. So, any questions, again, before looking at these last couple of rotational concepts this week? All right, so last two spinning things. First of them is angular kinetic energy. Pretty much every form of motion takes some form of energy. If you can see something moving in some way, shape, or form, it has energy, it needs energy to be able to do that. Linear kinetic energy is what allows things to move in straight lines. There's other forms of motion as well. Technically, heat is a form of motion on the atomic level, and objects need thermal energy for their atoms to vibrate at a given temperature. And additionally, spinning takes energy. If I hold the wheel and do this, we've discussed, is this a form of motion? Yes, it's not a trick. This is a form of motion, but is it moving in a straight line? Does it have a linear velocity? No, there's no linear v that we can measure from this because the object is technically stationary from that frame of reference, from a linear frame of reference. We can tell it has energy, and in fact, I did work to give it energy. I'm exerting a force as I move the wheel as I move my hand some distance. So I'm doing work, I'm giving it energy, it's just not in the linear kinetic form, it's instead in the angular kinetic form. Spinning takes energy. And that form of energy is called angular kinetic energy. So Ke with this little theta subscript attached to it, that's just to tell you it's spinning instead of moving in a straight line. And the rest of the formula is a direct one-to-one comparison to the normal kinetic energy formula. Normally, linear Ke is 1/2 mass times velocity squared. Instead of mass, we've got moment of inertia, and instead of velocity squared, we've got angular velocity squared. Once again, same formula, just rip out all the meters and replace them with radians and Greek. As a concept, how does this notion feel? All right. Now, angular kinetic energy makes itself known in a few weird ways. Most of the moving objects we've been looking at up until the rotation stuff have been moving in straight lines, and we've tried to avoid them having rolling parts. Wheels are weird in that for a wheel to actually roll along the ground, it needs both linear kinetic energy and angular kinetic energy. If it only has linear kinetic energy, it'll just move in a straight line while sliding forwards and not rolling, because it needs the angular version to spin. On the other hand, if it has angular kinetic energy but no linear, it's just going to spin in place. So to actually roll forwards, you need both forms at once, which can create kind of an interesting scenario, again, if something is rolling and there's only a fixed amount of energy that you can give it. We've done questions similar to this. This is going to be a sphere rolling down this ramp. And we've done similar questions where, say, we were comparing GPE to KE as the energy transforms as something, say, sliding down a hill or just falling possibly. We've done energy transformations where the GPE turns into the kinetic energy as you slide down. What's weird if the object is rolling, though, is that some of the energy becomes linear and some of it becomes angular. It needs a little of both to be able to move correctly. And if it's rolling rather than just sliding, you do have to account for both. So in this particular question, we're kind of going back to chapter 5 energy manipulation real quick, but we're going to factor in angular kinetic energy now. We're going to take this sphere and roll it down this hill. It's starting at an elevated position of 2 meters, and that means in that position it's going to have what form of energy before it starts moving? Gravitational potential. Yeah, it's above the ground and it's going to descend as we let it go. So initially, what it's got is just GPE. Total energy initial equals total energy final. Initially, our before state being before we let it go, it's just sitting there, it's got GPE at first. So again, flashing back to chapter 5, energy conservation, total energy initial equals total energy final. Initially, all we've got is GPE. Now, as we release this sphere to let it roll down the ramp, we're going to consider our final state to be once it reaches the ground. And when something as something rolls down an incline, it tends to speed up going from top to bottom, right? So as the object descends, what's going to happen to its GPE? Exactly. GPE will decrease as the sphere rolls down the ramp because even though it's not falling, its height is still decreasing. And instead, what type or types of energy does it have in place of that once you get here? Kinetic, because now it's moving. It has a velocity. Now, again, when last we checked in this genre of question, we didn't really use rolling objects. We caused objects to slide either on a frictionless surface or just fall straight to the ground. And if an object is just sliding or falling, then all it has is linear kinetic energy. But this sphere is rolling. So it additionally, oops, I put an I, it's supposed to be an F. It's additionally simultaneously going to have angular kinetic energy. It's going to need both forms to roll forwards. Again, only true if it's rolling. All the previous questions we did where something was sliding or falling are still true. This is a weird complication because it is rolling. So since it's rolling, we have to account for the fact that some of this initial GPE is going to have to enter the angular state instead of the linear one. And this actually means rolling it down the ramp has a lower top speed than sliding it down the ramp. Yes?
What is on the left side of the
GPE initial. Is that easier to read?
slide?
Slightly. My problem is I forget most of my markers need replaced until I come into the room and have to use them again. As soon as I leave the room, the problem stops existing in my brain. We don't throw any of them away because they're all about as if, there we go, that's got the most ink. Okay, is that easier to see? Excellent. So, once again, we're going to investigate how the initial gravitational potential energy is going to transform into both of these forms of kinetic energy because it is specifically rolling and not only sliding in a straight line. And again, this only happens when you're rolling. When you're sliding, all the energy can turn directly into the linear form. But if you're rolling, that actually actively decreases your top speed, because you have to sacrifice some of your linear kinetic energy to make angular instead. If this term wasn't here, it could all become linear kinetic energy and that'll drive up your top speed. But if you have to sacrifice some of it to spin, that drives down your top speed. Now realistically, in a world with friction, it's still easier to roll down a hill than to slide down a hill because friction is kind of a pain. So this is really only true in a frictionless world, or as close to frictionless as you can get. I'm going to try to build something by Monday to try to demonstrate this if I can. But for right now, any questions about this as a starting point? Okay. So, on the initial side, GPE is once again mgh. Kinetic energy is going to be 1/2 m velocity final squared. And then angular kinetic energy is 1/2 times moment of inertia times omega squared. The thing we ultimately want here is V. We want to know how fast this thing is going to move. So what we're after is VF. We want to know that final speed. And looking at the list of things that we do know the mass of the object. That's listed as 1 kilogram. G is always just 9.8. Starting height, I'll specify each initial. Starting height was 2 meters. Yeah, 2 meters. Mass again, we want velocity, and then we get to the angular kinetic energy. We don't have I or omega yet. First thing we're going to need to do is figure out what to use as I, and conveniently, we know this thing's a sphere. We know its shape. We can check this chart for moment of inertia. The formula for a solid sphere's moment of inertia, as long as it's spinning through its own center, is 2/5 mass times radius squared.
Why 2/5? That's random.
It is pretty random. Every shape has a slightly different fraction on the front, and I do admit it does feel kind of arbitrary. I don't have them all memorized because it feels kind of random, I admit. I don't have a good explanation for why it's
That's
2/5,
fine.
sorry. It's
No,
just
It
a
was
lot of,
more of a rhetorical question.
yeah. And again, that's why I would never ask you to memorize these. This chart's in your formula sheet because I cannot usually remember, like, why is it 2/5? We never use fifths in here. So, I'm sorry I don't have a more satisfying answer. So, I'm just going to kind of show that we're plugging that formula in instead of I. So 2/5 mass radius squared. So that's eliminated I as an unknown. We know mass, we know sphere radius, so I is no longer an unknown. We can plug in things that we know instead of it. But we still got to deal with omega. Remind me what omega stands for. Angular velocity, yes. Angular acceleration is alpha, which looks like A. Weirdly though, angular velocity doesn't look that much like a V, unfortunately. At least, I don't think it does. So, we don't know angular velocity, but it is conveniently related to linear velocity, correct? Because if something's rolling forwards, it's spinning and moving forwards at the same time. So we can actually replace that omega with something in the form of V. Oh, that was in my previous slides. If you glance at your formula sheet, that middle column between linear and rotational again, V equals R times omega. We have omega in the formula, we want V in the formula, because V is what we're after. And we can use that to turn omega into V. So, just put it up on the board so it's easier to read. I'm referring to this part of your formula sheet. the formulas that let you transform angular into linear and vice versa. We can use this to get omega out of our formula and make it about v instead. Does that make sense? So just rearrange this to become omega equals v over r. Just tells us the relationship between its angular speed and its linear speed. It's true for all rolling objects. And so instead of omega squared, we're going to write in the final squared over r squared. Since the entire omega was squared, we have to square everything we are putting in place of it. I just went ahead and applied the square to both the numerator and denominator. After all these substitutions, VF is now the only unknown left. How's that feel? Now, interesting, what I find interesting after all of that is, after replacing I with this and omega with this, if we simplify this just a tiny bit, notice we've got r squared in the numerator, that was part of I, and now we've got an r squared in the denominator from the omega. And so those are just going to cancel out, which will turn this entire term ultimately into 1/10 mv squared, which is almost the same as the linear formula, slight alteration. So the formulas are connected. The angular energy is still tied directly to the linear energy. I find that a neat comparison, at least. But I'll just note the r's cancel, so we don't really have to deal with the r squared here. And we start plugging things in. Sphere. Sphere's mass was 1 kilogram, magnitude of 9.8, starts at 2 meters above the ground, equals 1/2 times mass of 2 times the unknown final velocity squared that we're looking for, plus, that's not 1/10, that's 1/5. 1/5 times mass of 10. The r's canceled out because they're both squared and one's in the denominator, so that just leaves the f squared again in that term. Yes?
Why is that mass 2 and the first one 1?
What? Oh, that's because I made a mistake. Sorry. Thank you for, please call me out when I do that, or do something like that. Yes, you're right. The mass is 2, and I wrote 1 by accident. Wait, no. Not only do I write things down wrong, sometimes they just come out of my mouth backwards. The mass is 1, I wrote 2, I apologize. Does it look right now? Okay, sorry again. I'm having a pretty rough day. VF is now our only unknown, so we're set to solve for it. Any issues or questions arriving at this state?
Is it 1/5 or I thought you said it was 50? Okay,
That
so
was
it was
2
2 over
fifths.
10. It was 2 over 10. You simplified.
Yeah, 2 over 10, 1/5. I think I said 1/10 a second ago, but it is 1/5. So again, I combined the two fractions here into a single fraction, and I canceled out these r's because they just divide out. Well, one divides out the other. left side should condense down to just 19.6. On the right side, we've got 1/2 times VF squared plus 1/5 times VF squared. Note again, if this object was not spinning, if it was only sliding, this term wouldn't be here, and that would end up increasing the final speed. We got VF squared in 2 places. We can use the distributive property to combine those. So VF squared times open parentheses 1/2 plus 1/5. Plus 1/5 ends up being 0.7. So divide 19.6 by 0.7 and then take the square root. And the sphere's final linear speed should be about 5.3 meters per second. Questions, issues, complaints? All right. Now, I just did a second calculation on my calculator as well. Because again, if this object was not rolling, this term wouldn't be here, which at the end of things would eliminate this 1/5. That's what the 1/5, that's what the kinetic energy adds, is this extra, that's what angular kinetic energy adds, is this 1/5 right here. I double checked, I just took it out in my calculator real quick to find a second answer. If this thing was sliding on a frictionless surface instead of rolling, its final linear speed would be 6.3 instead of 5.3. The fact that it is rolling takes up some of its energy. In a frictionless world, sliding would be easier than rolling. In a world with friction, though, rolling ends up being the easier option most of the time. But if the world was frictionless, the most efficient thing would just be to skate around everywhere instead of things having wheels. So, what this means for you guys is, if I ever ask about a rolling object that is very specifically spinning, this is another form of energy that the object can possess, and it's one you might have to factor in. Yes?
So in this case, the angle at which it's sliding at doesn't matter?
Not if we're just comparing start to finish.
Okay.
Because initially, and again, frictionless world, we're assuming for simplicity's sake, frictionless ramp. Its starting height, regardless of the angle of the ramp, determines its initial energy, and its ending height means that all that initial GPE is gone and had to turn into some form of KE. So, angle of the ramp doesn't quite matter if you're just comparing beginning to end. Beginning, GPE, end, it's all turned into KE. The ramp just kind of changed the direction. Because if the ramp wasn't there, it would fall straight down, and it would just be at a linear speed pointing this way. What the ramp did is it just changed the direction of the final speed, assuming there's no friction.
Okay.
Does that answer the question?
Yes.
Okay. Any other questions for right now? Okay. Now, last rotational concept is going to be the notion of angular momentum. I'm going to step out of the room for just a sec. I'll leave this up so you can copy it down and ponder it. There's a piece of equipment I want to find real quick to try to demonstrate something. this door from the beginning. Okay, ready. So, define linear momentum again for me.
Mass times velocity.
Mass times velocity, and it is a basic measurement of how much an object wants to keep moving in a straight line in a single direction, unchanging forever. And the harder it is to stop. Turns out the same is true for rotating objects, because if something is spinning, it wants to keep spinning in exactly the same way forever. If I take this wheel and I physically make it start spinning, it wants to stay at this speed. And if friction didn't exist, would it keep spinning like this forever?
Yes.
Yes. That's the problem with perpetual motion. We'd have it if it wasn't for friction. But an interesting thing happens for angular motion versus linear motion, because when something is just moving in a straight line, that straight line is it. It's just a one-dimensional vector in a straight line forever. But rotation's kind of weird, because even though a lot of the vectors point clockwise or counterclockwise, technically the object is kind of moving in a two-dimensional plane, because parts of it are moving horizontally in the x and parts of it are moving vertically in the y. So rather than just wanting to move in a straight line, this thing wants to keep spinning within a single constant two-dimensional plane. And it really hates if that plane tries to rotate. Which means that if I try to turn this wheel while it's spinning, it's going to fight me on it. It's going to argue with me and hate changing in that way. So it pushes back against me, causing it to, at times, just wobble uncontrollably. All I'm doing right now is trying to turn it like this, and it is literally fighting with me because it wants to stay in the same 2D plane. In extreme case, why did I stop it? In extreme cases, it might be fighting me so much that it will defy gravity. Would it do this if it wasn't spinning? No. But since it is spinning, and since it wants to keep spinning in the same flat 2D plane, the wheel itself is going to push against its own axle to try to stay oriented in that plane rather than just falling straight down. This is the gyroscope effect. If something is gyroscopically stable, it's because it has something spinning inside of it to try to keep it oriented in that plane. And if you try to force something spinning in a given plane to change, it's going to fight you. Behold. Ah, nuts. Well, as I move the wheel, it is making me spin in the stool. It is fighting against me while I do this. Ooh, there we go. I didn't kick off the ground. The wheel is doing this to me. Trying to make it happen again. There it is. The wheel is doing this to me. And you can try it yourself if you want. Places you might see this, again, are gyroscopes and tops. Those objects want to stay spinning in the same plane. So if you get a top spinning and you flick it, it might move away from you, but it will eventually right itself as long as it's still moving, because its angular momentum compels it to keep spinning exactly the same as it already is. It's also why, when you were first learning how to ride a bike, you were probably told not to do this to the handlebars. Does that sound familiar? Because when you do this, you're suddenly changing the two-dimensional plane of that wheel, and you're probably going to face plant. Instead, to turn a bike, you tend to just lean into the turn, right? A more a very more subtle change to the plane the bike's wheels are in. But because the wheels want to stay upright, you can actually throw a bike forwards and it'll roll on its own while staying upright without a rider. Because the wheels want to remain vertically oriented as long as you're spinning. There's another interesting side effect to angular momentum that I want to show you today before we break. We'll talk about this a little more on Monday. It's fine. See, when we're looking at linear momentum, mass times velocity, we were usually looking at changes in velocity because an object's mass doesn't usually spontaneously change, right? Like matter doesn't just appear and vanish at will. But the thing about moment of inertia, I'm going to tap back real quick, angular momentum, L for some reason, doesn't just care about mass, it cares about moment of inertia. A moment of inertia does depend on mass, but it also depends on radius. If you look at that list of formulas, they're all m times r squared times some fraction. So mass might not spontaneously change, but radius can. If I'm spinning and I've got my arms out like this, I can change my own radius by pulling my arms in. And if I'm spinning, I have a certain amount of angular momentum. If I pull my arms in, I am changing my moment of inertia, not because my mass changes, but because my radius changes. And if you change moment of inertia on the fly, velocity has to change so that your momentum stays the same. So my last demonstration before we break is, I'm going to spin myself on this stool with my arms out. And with my arms out like this, I have a big moment of inertia, so I'll have a small angular speed. And then once I'm going, I'm going to pull my arms in. That's going to decrease my radius, decreasing my moment of inertia, and my velocity is going to have to rise to keep my angular momentum constant. Ready? Thank you. I did not notice. All right. So, note my speed with my arms out. And 3, 2, 1. Get out! I should not be doing this in a stool without a back.
It's like the ice dancers do.
Exactly. That's how they speed. That's how they speed up. They pull in all their limbs. Oh, I'm dizzy. Pro tip: spin once in the other direction to fix dizziness. I believe dizziness happens because your brain fluid is still spinning, because its own angular momentum tells it to keep spinning. Brain fluid or inner ear fluid? I'm not a biologist. All right, we'll look more at the math for this next week. Let me know if you have any questions over the weekend, and have a great weekend.